Precalculus, Chapter 6.3, Parametric Equations. It's going to be a pretty short video just introducing what parametric equations are and showing a little bit of their uses and what we're looking for here, and also introducing you to the calculator display in use for parametric equations. Okay, this first slide here is a Ferrari, and we have a cliff overlooking a body of water. It so happens that one of my current year's pre-calculus students, Will, tells me of when he and his father went to Las Vegas and rented a Ferrari and drove that Ferrari enormously quickly on the roads. And here nearby to Las Vegas is the Boulder Dam, which behind it is Lake Mead, and you see these cliffs overlooking. Let's make an assumption that we have this car that is going to go off this cliff, kind of like Thelma and Louise, if you've seen that movie, and they have the Lake Mead below. You have 100 feet is the height of the cliff. You have this car that is going off the cliff, and when it leaves the cliff, it is going at a speed of 120 miles per hour. Now, I happen to have worked out that 120 miles per hour converted to feet per second is going to be 176 feet per second. What a parametric equation does is it is two equations. One equation represents the x motion. Okay, so we're going to have this equation here is going to be, we can consider this like an xy coordinate plane. And here's going to be at the base of the cliff, we have the point 0, 0. And we have up here at the edge of the cliff, we have it's like the y-intercept, 0, 100. And then x is out this direction, so that the path of the car is going to be like this. And we're going to try to find out how far out this car goes before splashing into the water. Well, to do that, there are two equations that are involved. There's an x equations. There's an x equals, and we have 176 feet per second. So x is going to be 176 times time. Now we're assuming no drag due to the air resistance, which in the real world, of course, there would be, but we'll just assume there will not be. And then there is a y equation, and the y is going to be starting out at the y-intercept of 100 feet, so 100 feet, and then we are going down due to the force of gravity, which is going to be minus 16 t squared. And so what we can do is set up a table where we have time, and we have x and y. And so it's this kind of table here. And we're going to go and put in some numbers and just kind of see where we are. Okay, at time equals 0, we're going right off the edge of the cliff, so x is going to be 0. And we can do it according to this formula here. And y is going to be 100, because if t is 0 here, y is 100. Now at t equals 1, after 1 second, how far will we have gone? Well, it's going to be 1 times 176, which is going to be 176. And then we have y is going to be y equals 100 minus 16 times 1 squared, which is going to be 84 feet. And at 2 seconds, we're going to have 176 times 2. And what is that going to be? 300 and, let's see, that's 352, isn't it? I think so. Is that right? Yeah, I think it is. Okay. Yeah, because 20, yeah, that's going to be right. And then for this second y value, we're going to have y equals 100 minus 16 times 2 squared. And 2 squared is 4, so it's going to be 100 minus 16 times 4 is going to be minus 64 equals, so that could be 32 feet. No, 36 feet. 36 feet off the ground, so 36. And next, at 3 seconds, how far out are we going to be? Well, if we add another 176 to that, let me just write out here. We'll have 8, and then 12, and then 5, so 528 feet. And so we have, and as far as the vertical, y equals 100 minus 16 times 3 squared, which is going to be, I'm just going to go to a calculator, I give up. 100 minus 16 times 3 squared. We're going to get negative 44. And so what we're going to do is we're going to be below the surface of the water. So basically, we're going to have to do a little more analysis, probably on our calculator, to figure out exactly where we're going to be. You could, if you wanted to, set, if you set this y equals, if we set 0 in the place of y equals 100 minus 16t squared, we can solve this equation using the square root method and get an exact answer that way. But we're going to go to the calculator a little bit later, do some more analysis on this one. By the way, neither Will nor his father are injured in this example here. They safely parachuted out to the water below as part of their great adventure. All right, here is a parametric equation, and what you have, it's sort of is like a system of equations where you have x equals an equation in term written in t as an independent variable, and y is an equation written as with t as an independent variable. And this together, when you have these two equations, x and y, this is called a parametric equation. And sometimes you'll see it called parametric equations because there are actually two of them, but they can just call it parametric equation too, so it's sort of can go either way. But what you try to do sometimes is a technique to graph this is one that's called eliminating the parameter. Okay, parameter. And parameter, you can see, I hope, is a word that is similar to parametric, right? Well, the parameter is going to be t. So typically what we'll do for this is we'll take, if you want to graph this in your as a regular equation in your calculator, you can take this first one, x equals t squared minus 2, and you can solve for t. And so t squared is going to be equal to, if we add 2 to both sides of this equation, t squared is going to be equal to x plus 2. And taking the square root, t is going to be equal to the square root of x plus 2. Now, is that a correct one? Well, almost. What you have to do is going to be plus or minus x square root of x plus 2. And then what we do is we take this plus or minus square root of x plus 2 and plug it back in to the second equation. So y is equal to 3, and in place of t, we can put here plus or minus square root of x plus 2. So that's what it looks like. And so what this is going to be, it'll be y equals 3 times square root of x plus 2, and also y equals negative 3 times square root of x plus 2. And we can graph this in a calculator, and let's get our calculator here. 3 times x plus 2, and then down here, negative 3 times square root of x plus 2. And then if we graph this equation, what is this calculator doing to me? There it is. We can see this calculator here. We can trace the position, but you can see there's no time involved here. And let's go to trace. So we can trace this top equation here like this. Okay. Now we can scroll down this bottom one here and similarly scroll here. So we have to have 2 functions to graph this one equation in the calculator because of what the vertical line test requires us to have 2 functions to graph this parametric equation. And we call this form here, when we eliminate t, let me make sure the calculator is going to show up all the way. Move it over here just to be sure. Okay, what we call is, this one is called the rectangular equations. Now, rectangular is another way of saying equations with x and y. So rectangular, like with on a coordinate plane, right? Rectangular equations, parametric equations. So sometimes you're going to be asked to go from a parametric equation and convert that to a rectangular equation. But when you do that, you're going to eliminate that parameter t in so doing. Now let's go back to our calculator and graph this as a parametric equation and see what we get. Now I'm going to go ahead to mode, and you see right here this line where it says function. We go to the right where it says parametric, place enter, and there we have it. And we go back to y equals, and then you see these equations in terms you haven't seen before perhaps. So we're going to put here t squared minus 2. So you press this x key here, and you'll get a t. And you square minus 2, and then y is equal to 3t. And then you graph this equation, and you see just the top half of it. Now, the reason you see just the top half of that is if you go to the window, your standard window for a parametric equation starts with t minimum equals 0 and t maximum equals 6.28 so. That 6.28, I want you to think of what that is. And I'll tell you later if you can't think of it now, but you can tell me next Thursday in our live chat for those of you who are there. And then otherwise, it's pretty much the same as the standard window settings we can change. Now, if we want to see the whole equation, we can go to, or we can go ahead and put a time less than 0. So if I put in here negative 6.28, let's see what that gives us when we graph. Well, it gives us a fuller curve, similar to the one we did earlier with just the rectangular form. And we can trace this curve, and we're given a t of negative 6.28. We go to the right, and you see the t changing, okay, and the x. So I'm going here, and you see as we go in this direction, so when you go to the right, that means t is increasing, t is becoming positive, and then you go like this. And you can go to your window if you want to get a little tighter view. You can make t steps smaller perhaps. I'm not sure how easy it is to do that. Let's try 0.1, see if that'll work. And we go back to graph and trace, see if that makes a difference. I don't know that will. Yeah, I'm not sure how much good that did to us, but anyway. I want to do one more thing here before we go. As I want to get back to the Will's situation where he and his dad are taking that joy ride off that cliff into the beautiful Lake Mead below. And so the x we have is going to be 176t, and the y is going to be 100 minus 16t squared. And so we're going to set our window to be able to see everything. Well, the x minimum is fine. Our x maximum we want to have way out there. We know that probably is going to be 500 feet or so. We'll put x scale of every 50 feet. We'll say y minimum. We'll put like negative 50 here. And the maximum, we got to have at least the height of the cliff. We'll go every y scale every 10 feet. And so when we graph this, we should see the whole trace path. And we do see it, don't we? Okay. So I think these are every 50 feet out here. So 50, 100, 150, 200, 250, 300, 350, 400. So about almost 450 feet out. And we can trace this. And let's trace it, see what we get. Okay. I have t set at negative 6.28, which we kept from the last time. I'm going to set this to 0, just to start from a better place. We press, oops, I don't want that. Let me do that again. Okay, we'll go to graph, trace. Okay, there we're starting at 0. So we can just go right here and looks like t is advancing every tenth of a second. So here at about 2.5, exactly 2.5 seconds, we're 440 feet out, and y equals 0. So we know the answer to that question is 440 feet. So let's go back here. So how far out? 440 feet. And we could have solved this equation, like I told you earlier, if we had, that'll be the t value, but then we'd have to plug that back into x, and we would get 2.5 seconds. So if we plug in 2.5 into this equation here, so x equals 176 times 2.5, we would get 440 feet. So we're going to have a chance to do a lot of analysis with our calculator. And one thing that's really, really nice about this section is that we're able to use it for a lot of the physical applications, and particularly these parametric equation sports problems. There'll be a bunch of them. We're going to use angles a lot, and it should be pretty fun, and we'll be able to do a lot on these calculators. I think it should be pretty intuitive, and I think a pretty fun part of the course. So good luck, and we look forward to working some parametric equation problems and situations later this week. Thanks for viewing.